Hello, and welcome to VLMD Rounds, a podcast for bringing the art and science back to medicine. I'm Dr. Vivian Lowe. Now, this episode deviates from my usual format, and it arose from a request by a friend who asked if I knew Peter Attia's podcast. I had heard of Dr. Attia, but confessed that I'd never listened to his podcast. My friend said he talked a lot about cholesterol and lipoproteins and wanted to know what I thought of his content. Was it legit? What did I think? He just wanted my opinion. So, as a favor, I said sure and went to his podcast, which is called The Drive. I scanned the titles and came across a series he did with Dr. Thomas Dayspring, a deep dive into cholesterol and lipoproteins in 5 episodes, and I figured this would be a good place to start. I admit I kind of listened to it in the background as I went about my day because it was the only way I could fit it into my schedule. I'd listen while I was driving, doing errands, having lunch, whatever downtime I had, and found myself stopping to jot down notes for my friend. Now, strangely enough, around the same time, other people started asking me the same thing. Do you know Peter Attia? Have you heard of him? What do you think about his take on cholesterol? Can you let me know your thoughts? Friends, people I met at events, meetings, colleagues, all wanted to know the same thing. So much so that I thought, hey, I'll just do an episode on this. Okay, so what I thought would be a simple listen and short discussion with my friend turned into a real project. I'd be driving and listening and then almost swerve off the road because I'd be so distracted by something I heard. And I'd pull off to the side, scribble down some points so I wouldn't forget, get back to driving. And then when I had time at home, I'd listen again to find those timestamps, fact check things just to make sure I hadn't made a mistake, and then write those down. Needless to say, this took a lot of time, and the project got spread out as I went down rabbit holes and went into deep details. And then one day I realized that I'd never be done at this rate. So I changed my approach and decided I wouldn't check everything and go into detail and everything, just the things that immediately jumped out at me. And I'd give a general overview of the series. And so here we are. For those of you listening in to the audio of this podcast, I want to point out that I have this on YouTube with slides to illustrate my points. So if you want details on studies that I reference, you can check it out on YouTube. I also put up parts of the transcript from the interview to make it easier to follow along. All right, now some background. Let me get my notes. Dr. Peter Attia got his undergraduate degree in mechanical engineering and applied mathematics at Queen's University at Kingston, Canada. He went to medical school at Stanford and did a residency at Johns Hopkins in general surgery. After that, he did some research at NIH, and he now lives in Texas, where he has a medical practice. So somewhere in there, he did a medical residency. And now he has a medical practice centered on anti-aging and longevity. He has a recent book out called Outlive, The Science and Art of Longevity, which was co-authored with Bill Gifford. Now, Dr. Thomas Dayspring is a renowned lipidologist who practiced primarily in New Jersey and was the chief scientific officer at 2 labs. He's been the associate editor for the Journal of Clinical Lipidology. He wrote countless papers and book chapters and has spoken on lipid science around the world. Right, since so many people ask me for my opinion, I decided to have a checklist for what I was basing that opinion on. The number one thing was, of course, accuracy. Now, when I came across things they said that I was surprised by, I didn't rely on my own memory. I did look things up, I got my references and so on. To be fair, I made sure that the majority of my references predated the interview because that would have been the information that was available at the time, about 3 or 4 years ago. So most of the references are from the early 2000s, I believe. I did add some more current references to provide more information to all of you because beyond reviewing the interview, I intended this episode to be a jumping off point for more interesting topics. Okay, so accuracy. The next thing was consistency. Here, I was looking to see if certain things said at one point would contradict other things said at a different time. And then I had a category called significance. And this is because I feel that it's important not just to go into the details of the science, it's vital also to step back and look at the greater implications of those details. Significance also addresses scope a bit, I think, because sometimes we focus only on one or two aspects of something. And as a result, there's a danger of missing the bigger picture of what might be going on. Now, I wanted to align myself with the intention of the series. They had invested so much time, long hours of recording. And the point of this episode is really not to contradict them, but to maybe amplify and clarify their discussion. So it was important to stay aligned with their intentions. Now, it turns out that Dr. Attia wanted to provide education to physicians.
To say that you could learn more in the next 7 hours, meaning episodes 1 through 5, than you would learn in a lipid fellowship. And I suspect that many people who are studying in a lipid fellowship will find great value in this. That's the level of detail we go into. And at the same time, if you're a patient, if you're a primary care physician, I think you will still find this incredibly valuable. So this was a little more work than usual to prepare for it, to record it, to edit it, to break it down, to do all of the things we did. But I believe it's worth it, and I am so happy to have been able to have done this because I think there are a few things that I get more pleasure out of than sharing Tom's knowledge with other people.
So you see, a lot of work went into it. And, I've never been in a lipid fellowship. So, I was really looking forward to this. And I think Dr. Dayspring also was very interested in education.
Today.
Amen. And I'm sad there's so much what I consider inferior lipid care being administered by healthcare professionals in the United States, but there's nothing I can do about that. It's try and teach them one at a time or expose my writings and other people's writings and the data on this as much as I can.
And, besides education, he is very invested in the rigor of academic work.
Reject a paper instantly that uses improper lipid metrics to measure that. So let's please all you, don't identify yourself as an ignoramus.
Ooh, I hope I don't identify myself as an ignoramus. Um, you know, these are two very distinguished gentlemen, and I have to admit, I was really nervous about doing this episode. The two of them have, done so much more and know so much more than me, and I was honestly a little intimidated when I thought of doing this episode. And then I thought of, one of my my favorite scientists, Richard Feynman. And I learned of Richard Feynman when I was a kid. I read his memoirs, and I, was always taken by him. This is a picture of him playing the bongos, and he was a bit of a crazy man, but he had a very good mind and an excellent mind. And I found a list of principles that scientific principles that he abides by that actually kind of, help encourage me through this episode. So he said before, have no respect whatsoever for authority, forget who said it, and instead look at what he starts with, where he ends up, and ask yourself, is it reasonable? And then if we suppress all discussion or criticism, proclaiming, this is the answer, my friends, man is saved, we will doom humanity for a long time to the chains of authority confined to the limits of our present imagination. And then I learned very early the difference between knowing the name of something and knowing something. And then the real problem in speech is not precise language. The problem is clear language. This is the principle of science. If there is an exception to any rule, and if it can be proved by observation, that rule is wrong. So, some of these principles really just motivated me and heartened me and encouraged me on the journey. All right, enough of an introduction. Let's go. So the first part of the series, part 1, we get introduction to Dr. Dayspring, and we talk about his life and his career. And then about an hour in to that first part is where they start their discussion on lipidology. And this is where I first pricked up my ears.
Lipoproteins are on our cell membrane. Every cell membrane in your body is phospholipids. And what nobody seems to know is most of your phospholipids are made in the liver, or they're made in the small intestine. Phospholipids. And what is the surface of every lipoprotein? Phospholipids. Where do the phospholipids come out of? Lipoproteins produced in the intestine or the liver. So what are the biggest lipoproteins? Because they would have the most gigantic surface area. Chylomicrons coming out of your gut, very low density particles coming out of your liver. So we all talk about, they're delivering cholesterol, they're delivering maybe triglycerides, because they're very triglyceride, but they're delivering phospholipids.
Okay, so this was a bit of a surprise for me, and I was a little taken aback because I really had not known that most of the phospholipids are made in the liver or in the small intestines, and that lipoproteins were primarily for delivering phospholipids. And he says this quite clearly in the interview. So this is an article from the Journal of Lipid Research 2009, and it looks at phospholipid synthesis, and it turns out this happens in the endoplasmic reticulum of cells. It says bulk membrane lipid biogenesis in primary cells largely occurs in the endomembrane, which includes the ER and the Golgi. And then here, are the different steps involved in phospholipid synthesis. Here's another paper from 2014, phospholipid synthesis and transport in mammalian cells. And it says in there that all nucleated mammalian cells make phosphatidylcholine via the CDP choline pathway, also known as the Kennedy pathway. And this is what I had learned, and this is what I had been thinking all this time, that it wasn't specific cells in the body that made phospholipids. It's really most mammalian cells. Here's another study from Molecular Biology of the Cell, 2002. Phosphatidylcholine is synthesized almost exclusively through the CDP choline pathway in essentially all mammalian cells. And then as to this part where he talks about the lipoproteins delivering phospholipids and not delivering cholesterol, a little bit of triglycerides, but they're really delivering phospholipids is his point. And then he goes on to say they jump on a protein here. So let's listen to that bit.
Decrease in diameter of the lipoprotein is occurring, or they jump on a protein that evolution has given us called phospholipid transfer protein, which then takes all those phospholipids and brings them to cells that say, hey, I need phospholipids.
Okay, so I thought maybe we should look at the phospholipid transfer protein. And it turns out that besides phospholipids, phospholipid transfer protein efficiently transfers diacylglycerol, alpha tocopherol, which is vitamin E, cerebroside, and lipopolysaccharides. And therefore, plasma PLTP is a non-specific lipid transfer protein. So despite having the name of phospholipid transfer protein, it actually transfers a lot of different lipid species. This is a paper from 2011. It's called a phospholipidomic analysis of all defined human plasma lipoproteins. And what they show here is the true importance and significance of the phospholipids. So they say the phospholipid content is one of the factors which have been suggested to contribute to the closer lateral molecular packing in LDL. The phospholipid composition in the surface of lipoprotein particles influences the binding of ApoA1, and that is the reason that ApoA1 is absent in LDL particles in vivo. And thus, here's the important point, plasma lipoprotein functions can be manipulated by protein or phospholipid compositions. Here's one from Biochemistry, 1989. And what we see here is the closer lateral packing in LDL is due at least to three factors: the difference in phospholipid composition, higher unesterified cholesterol content in LDL, a stronger interaction between cholesterol and LDL phospholipids relative to HDL3, right? And then this is another study where they say the binding of exchangeable APOs is influenced by the phospholipid content of the lipoprotein surface. So my clarifications for this point would be that all nucleated mammalian cells make phospholipids. It's not just the liver and the intestines that are involved in making phospholipids. Now, the main function of lipoproteins is unlikely to be delivery of phospholipids. There was just nothing I found in the literature that concurred with that, so I think it's unlikely. Instead, what we should focus on is that the phospholipid content determines the structure and binding of apoproteins to the lipoproteins, thereby influencing the function of particular lipoproteins. So those phospholipids are indeed really important, but it's not that the lipoproteins are delivering them necessarily to cells. The phospholipids themselves, their particular composition will influence packing and structure and association with other proteins. Next, we move on to lipid rafts. And I got really excited here because this is one of my favorite topics. So let's take a listen. And here we go.
Peter was just talking about that fatty acid makeup in the phospholipids becomes so crucial because saturated fats are straight, they're rugged, they don't bend. So it gives some structure to a phospholipid. If your phospholipids contain a lot of saturated fat, you got a strong cell membrane there that's hard to get through. But the real reason cells function and interact with the rest of the cells of your body is they signal each other. And signaling occurs because something occurs at a certain area of the lipid cell membrane that we're going to call a lipid raft, which is a specialized collection of special phospholipids with a little bit of free cholesterol interspersed. But the structural positioning that a phospholipid takes up, if you have several double bonds in that thing, if you've ever seen a 3D view of a phospholipid that's got several double bonds and it takes up an incredible amount of space, so its two legs spread out, and you change the structure of the cell membrane, and that structure of that area called the lipid raft allows certain cellular proteins to locate there. And those are all our receptors that pull things into cells or extrude things out of cells.
So the fluidity of the membrane is highly, highly dependent on the nature of the fatty acids in the phospholipid.
Fluidity and the ability to shelter or let certain proteins be expressed in that area.
Okay, I think we need to take a close look at this because, as he said earlier, this is very crucial. Okay, it's very important to understand this because downstream, if we don't understand this, we might get a lot of things mixed up. So he is defining the lipid raft here. And let's see what he says. It's a specialized collection of special phospholipids. Okay, so he's saying it's phospholipids with a little bit of free cholesterol. All right, and it's these phospholipids that have unsaturated fatty acids, right, that make up the structure that is the lipid raft. So these phospholipids, they're filled with unsaturated fatty acids, according to him. And then in the next part, they talk about how the fluidity of the membrane is important and is due to certain fatty acids, right? And then Dayspring says the fluidity and the ability to shelter or let certain proteins be expressed in the area, because he talks about how the lipid raft is important for holding proteins, especially receptors. So they're talking about how the fluidity seems to allow for this sheltering. So now let's look at this paper from the Journal of Clinical Investigation, 2002. And this is by Kai Simons, who I think is really the leading authority on membranes and lipid rafts, all right? So let's see what he says in this paper. The difference in packing is due to the saturation of the hydrocarbon chains in rafts, sphingolipids, and phospholipids. So rather than unsaturated fatty acids, he's talking about saturated fatty acids in the raft, as compared with unsaturated fatty acids in the liquid disordered phase. Whenever people talk about membranes, you're going to hear them talk about liquid ordered phases and liquid disordered phases. The liquid ordered phases are corresponding to the rafts, okay? And the liquid disordered phases are the other domains of the cell membrane. So here's a diagram that I think will be helpful. You can see the lipid raft here in the center of the diagram. And note that the lipids here are saturated, right? The orange lipids here are saturated. And then on the sides, in the liquid disordered phase, we have the unsaturated lipids. Now, take a look also at the cholesterol. You will see that there's a lot of cholesterol within the raft structure, okay? And much fewer cholesterol molecules outside of the raft. So rather than have a little bit of free cholesterol, the raft structures are actually packed with cholesterol and sphingolipids. And we'll see here, lipid raft domains are usually defined as small, highly dynamic and transient plasma membrane entities enriched in, here we go, saturated phospholipids, sphingolipids, glycolipids, cholesterol, and so forth. Enrichment of these hydrophobic components endows these lipid domains with distinct physical properties, including increased lipid packing and order and decreased fluidity. So when we say liquid disordered, that's the same as saying that they have a lot of fluidity. But when we're talking about the rafts, we're talking about increased order, liquid order, and less fluidity. And the reason for this is, as they mentioned, the lipid raft is important for holding proteins and for holding receptors. Now, these are oftentimes very, very big, massive proteins. Some of these receptors, cross the membrane several times, right? And so they need a significant solid structure, stiff structure, where they can sit comfortably. And the sphingolipids, usually sphingomyelin, the sphingolipids and the cholesterol provide that, right? Every time you see a lot more cholesterol in that part of the cell membrane, that part of the membrane is going to be stiffer. It's going to be more rigid. it's going to be less fluid. And this is important to hold those receptors. Very crucial there. And this is from the Journal of Virology in 2007. And, again, he was saying that it has very little cholesterol, but you'll see cholesterol is a critical structural component of lipid rafts. And depletion of cholesterol leads to disorganization of lipid raft microdomains. This is one from the Journal of Biophysical Chemistry, 2016. It's called "The Stability of Lipid Rafts-like Microdomains is Dependent on the Available Amount of Cholesterol." And they say, results show that the addition of cholesterol significantly increased both the amount of insoluble lipid rafts-like structures and their stability. And the availability of a minimum amount of sphingolipids was necessary to produce larger amounts of more stable structures. However, the addition of phospholipids actually hindered the formation of lipid rafts-like assemblies, and those formed were generally less stable. So again, these lipid rafts are chock full of sphingolipids that associate very well with cholesterol. And then we have a lot of cholesterol in there as well. And they provide a rigid structure to hold a lot of these receptors and big proteins. And since they were talking about receptors, I thought we'd look at lipid rafts and insulin signaling. This is from Endocrinology and Metabolism 2002, put out by the American Physiological Society. So we've known about how insulin signaling is dependent on lipid rafts. This is another paper from the same year, 2002, Dynamic Association of Human Insulin Receptor with Lipid Rafts in Cells Lacking Caveoli. And they say in liver-derived cells lacking caveoli, autophosphorylation of the endogenous insulin receptor is dependent on RAF lipids. So the functioning of this insulin receptor is dependent on RAF lipids. Here's a more recent study. It's called Phospholipid Exchange, shows insulin receptor activity is supported by both the propensity to form wide bilayers and ordered raft domains. Long name. But basically, what they're saying is that when you have more of the sphingomyelins and raft structures as compared to the disordered or fluid parts of the membrane, which can contain more of the unsaturated fatty acids, they found that the propensity of lipids to form ordered domains, rafts, is required for high insulin receptor activity. Now, a lot of times you might hear of, studies that suggest that the use of statins is actually associated with diabetes, a higher risk for diabetes. And yes, it's important. No, it's not. No, it's just, something we don't understand. And I like mechanisms, right? So I'm like, well, is there a mechanism for that? Now, I'm not saying that this is the mechanism, so please don't go there. We don't want to be extreme, and I don't know. But this is something to think about, right? When we're thinking about what happens when we deprive the cell of cholesterol, when we deprive certain domains of the cell membrane with cholesterol. And again, this doesn't happen all the time, but under certain circumstances, when we are able to lower the cholesterol to the extent where it might impact the RAF structures, then we could have some actually lessening of insulin activity, insulin receptor activity, resulting in poorer, glucose management in the body. So my clarifications for this part, and this is really important, we want to remember that lipid rafts are more rigid, okay, than other domains of the plasma membrane. And they are packed with saturated fats and studded with cholesterol and sphingomyelin, right? And put that in. But the loss of cholesterol from the lipid rafts results in dissolution of the lipid raft. and the higher the amount of unsaturated fats, the higher the loss of function of receptors such as the insulin receptor. Okay, so again, I know that, I do go on a little bit about some of my favorite topics, and I do really have a lot of interest in signaling and lipid rafts, but I think this is an important point to make. All right, now we move on to this point that Dayspring makes over and over and over again in the series. He talks about how all cells make cholesterol. So this is important. So let's take a listen here.
Everybody talks of lipoproteins as if they're delivering cholesterol all over the place. That's what we have lipoproteins for. That's probably the last reason we have lipoproteins, because every cell in your body makes every cholesterol molecule it needs to do what it has to do, with a few rare exceptions. So if I'm a nose cell, I don't need some lipoprotein to come and deliver cholesterol to my cell, because I need cholesterol in my nasal cell membranes. That cell will make cholesterol. Every cell has the genetic power and the protein, the enzymology to make cholesterol to its heart's content.
And then later he says, I think I have it here.
Kidney or any place else, because those cells need cholesterol. Those cells will make it, or they'll get it by some free diffusion if they really need it, or absolutely virtually any cell of it absolutely needed cholesterol, because for some reason the synthesis was broken. Any cell could ultimately upregulate an LDL receptor, but most of them don't. So because they have no need for the cholesterol that's in an LDL.
Yeah.
All right, so as you can tell, he's quite passionate about this, and he's saying that every cell in your body makes every cholesterol molecule it needs to do what it has to do, with a few rare exceptions. And, if you need cholesterol, every cell has the genetic power, the proteins, and the enzymology to make cholesterol to its heart's content. And I took this from the transcript, so I know there are mistakes there. And then also, if it absolutely needed cholesterol because for some reason the synthesis is broken, any cell could ultimately upregulate an LDL receptor, but most of them don't. I spent a lot of time thinking about this, just because it tells me where I think the fuzzy thinking happened. So again, going back here, he's talking about the genetic power, the proteins, and the enzymology needed to make cholesterol. But if the synthesis part is broken, then they could then upregulate, these cells could then upregulate an LDL receptor, but most of them don't. So here you're seeing that he's separating synthesis from upregulation of LDL receptor. This is a paper from Arteriosclerosis, Thrombosis, and Vascular Biology, 2004. It looks at a transcription factor called SREBP2, or sterol regulatory element binding protein 2, mouthful, all right? And basically what you need to know is this is a transcription factor that is involved in turning on cholesterol synthesis. So what it does is this transcription factor lives in the endoplasmic reticulum. When cholesterol levels drop in the cell, it becomes activated. It then travels to the nucleus and turns on genes, right, to upregulate cholesterol. We want more cholesterol, right? So now when it detects that there's low levels of cholesterol in the cell, it moves to the nucleus and turns on genes that will help it accumulate more cholesterol. And it does this by initiating the synthesis of cholesterol, very important, but it also is involved in expression of the LDL receptor. It says here, expression of the LDL receptor, a key component of the cellular pathway for cholesterol uptake, is modulated as a function of cellular cholesterol content through SREBP-mediated transcriptional regulation. So main points here, again, actually covered this on episode 46 of this podcast, but SREBP2 is very important for homeostatic control of cholesterol levels in the cell. Once activated, it goes to the nucleus and turns on genes for de novo biosynthesis of cholesterol and upregulates the LDL receptor. It does both things. It turns on the genes, a set of genes that do both. Okay, it doesn't just say, eeny, meeny, miny, mo, we'll just synthesize today. We won't do the upregulation, all right, unless the synthesis part is broken. So here you understand that you can't separate those two processes. It's not like, oh, we have the synthesis part and then we have the upregulation part and they are separated. That's not how your cell thinks. And, obviously, cholesterol synthetic pathways are quite a lot to, work with. They're very complex. There's many, many names here that you have to remember. So in part 2, around the 40-minute mark, they go into what is cholesterol. They discuss cholesterol chemistry. And here, I just want you to look at the comments, if you have a chance, that were made by a viewer called Sobchak2, who identified as an organic chemist. So this person made some comments in the YouTube version of this about their cholesterol chemistry. So I don't want to take credit for that. So I thought, I'll put it up there and you can take a look. And I think it's important because they themselves recognize how important it is to be accurate with the chemistry.
Know some of this stuff.
Well, and that's the thing, you have to be willing to learn some of this chemistry. I mean, you have to steep yourself in biochemistry and understand because the significance becomes enormous. One double bond in one of these things completely changes its properties.
Absolutely. So I think because of the importance of this, that's probably why Sobchak 2 made those clarifications on YouTube. Right. So as I said, they talked a lot about how we make cholesterol synthesis, and they talk about the different pathways, the block pathway and the Kandach-Russell pathway. And it turns out that de novo synthesis of cholesterol is indeed highly, highly complex. There are many, many, many steps involved, at least 20 or so, regulated by numerous enzymes. And at one point, Peter Attia said, I remember learning this in med school, and it kind of brought me back to my own med school years. And I confess, I hated memorizing stuff for exams. So as they went on about the different enzymes and different points of the pathway, I was getting a little uncomfortable because I'm going to tell you now, I didn't do that. I was kind of lazy, and I just always tried to escape memorizing things. I actually have a very good memory, but I just hated memorizing stuff. Actually, you know what? I think Richard Feynman also hated rote memory. So maybe that's another thing we share. But, I would just do whatever I could to not like memorize, because I was that student. I was that kid that was always like, really? We have to memorize this? What's the point? Can't we just look it up, So it's a little bit whiny, I have to admit. I was lazy and I just didn't want to do the work, And then I would look at the pathway. I'd look at something like this, and my eyes would just glaze over, and I go, wow, that's a lot of work. That's a lot of work to memorize this. And then I think, wow, if it's so much work just to memorize it, I wonder how much work it would be for a cell to make this stuff. That looks like a lot of work. And then I would like go down rabbit holes, try to find this out. and read and look things up because I just was procrastinating and just didn't want to study, right? So kind of waste time. And instead of studying, I'd do something like that. But it turns out that, interestingly enough, it takes a lot of energy to make cholesterol. To make 1 mole of cholesterol, you'd need 21 moles of NADPH, 18 moles of acetyl-CoA, 36 moles of ATP. And if you remember that each, NADPH, is equivalent to 3 ATPs, when you run it through the electron transport chain, right? Then it turns out that you need over 100 ATP equivalents and 11 oxygen molecules to make 1 molecule of cholesterol. I mean, I'm exhausted just thinking about that's a lot of energy. So, if you were a cell and you had to get your supply of cholesterol, well, you could make it. You certainly could do de novo biosynthesis, right? So, if I were the cell, it'd be like, okay, yeah, let's make some dum dee dum dee dum. But I don't like cooking. I'm actually a decent cook, but it just seems like so much energy. So maybe here's my laziness showing again. But it seems like that's a lot of work to make it. So I might be more inclined personally to, think about outsourcing this and getting some takeout, right? So if you were a cell and you were trying to make cholesterol, increase your supply of cholesterol, for example, you could make some if you had, 100 ATP equivalents and 11 molecules of oxygen, just kind of, a spare change for 1 molecule of cholesterol. Or you might just save yourself some of that energy and, bring some cholesterol in from the environment. So my clarifications here are cholesterol homeostasis is regulated by the transcription factor SREBP2, which, when activated, upregulates de novo cholesterol synthesis and LDL receptor to bring in more cholesterol via LDL. It doesn't just turn on cholesterol synthesis only, right? You can't separate the two because it activates the genes that do both, right? And this is because cholesterol biosynthesis costs a lot of energy. As I said, over 100 ATP equivalents and 11 oxygen molecules per molecule of cholesterol made. So if you're a cell and you need cholesterol, right, you're always having to think about how much you have to spend, and you will probably might have to make some, but you'd also want to bring some in because it makes energetic sense to import most of your cholesterol rather than make it. And even pathogens, I note here, want to import it, right? So it's not just the cells in your body, but microorganisms in your body that might be invading you, right, would be very interested in cholesterol because they need the cholesterol to make cell membranes and so forth. And so they are always looking for cholesterol. And it's almost a hide and seek game, as you'll see later on. I'll talk about this a little bit. It's almost a hide and seek game here because your body's trying to deprive those organisms of cholesterol while those organisms are actively seeking out the cholesterol, right? So it's not just the cells in your body, but microorganisms, pathogens, and even cancer cells. Okay. So I think that's where it's important to think about this carefully and separate out the fuzzy thinking, understand that you don't separate synthesis of cholesterol from upregulation of LDL receptor. Whenever the cholesterol levels in your cells drop, then your cell's priority is, I just got to get more cholesterol. And it's going to do whatever it needs to get that cholesterol. It would synthesize some, but it would want to bring some in because that's going to cost a lot less energy. So the next part, I just want to go back to the point where he talks about how, we don't need to deliver cholesterol because every cell in your body makes every cholesterol molecule it needs to do what it has to do, with a few rare exceptions. And I thought, let's just take a quick look at those exceptions. Here are the cells that don't make cholesterol: sperm, right? They don't make cholesterol. And Sertoli cells, which actually make the sperm, they do make cholesterol, but not enough, right? And so they actually have to import cholesterol. They have to bring in cholesterol because they don't make enough for the process of spermatogenesis. So this is, again, outside of the androgenic function of testosterone, which comes from cholesterol. This is the fact that these Sertoli cells making cholesterol for the sperm cells, because the sperm cells are not going to be able to do that. And then we have red blood cells that also don't make cholesterol. So this is from Frontiers in Endocrinology. Again, very quickly, Sertoli cells provide large amounts of lipids used for spermatogenesis. In vitro, it has been demonstrated that Sertoli cells are able to synthesize cholesterol from acetate. However, this de novo synthesis is not a sufficient source of cholesterol to ensure spermatogenesis in vivo, and therefore it is necessary to import cholesterol from the blood circulation, because it's also a lot of work, a lot of energy, right? Red blood cells, they don't make cholesterol because they lack organelles. And remember, I said that cholesterol is made in the endoplasmic reticulum. So if you don't have an endoplasmic reticulum, then you're not making cholesterol. There are about 2 to 3 million RBCs produced and released into the bloodstream per second. And so there are about 20 to 30 plus trillion RBCs in your body. Okay, now this is a study from 2017. Sorry, I had a bit of a coughing spurt there. Let's get back to this. So it says here, approximately 50% of circulating cholesterol is carried in the red blood cell membranes, and tracer studies in humans indicate that the magnitude of the cholesterol flux through RBCs is comparable to the total efflux of free cholesterol from tissues. Now, this is something that both Dayspring and Attia are aware of. They both noted this in the interview. So they were aware that there's actually a huge amount of cholesterol carried in the red blood cell membranes, and really most of the cholesterol flux there through those erythrocytes is equivalent to what we see in the total efflux of free cholesterol. But at the same time, they don't seem to tie everything together. So where I talked about consistency is one of the bits. Let's have a listen.
Because actually there's no cholesterol in your red blood cells that are lipoproteins.
Yes.
And you're not making that zero by any means by using lipid drugs or something.
Okay, so you heard that was Dayspring, and he's saying there's more cholesterol in your red blood cells than lipoproteins. You're not making that zero by any means by using a lipid drug or something. So this is a study that came out of South Korea, and they found that statin use significantly increased the risk of developing iron deficiency anemia up to 5 times. And they felt that the iron levels of patients using statins should be monitored carefully. So I think that, there might be some influence of the statins there, not dropping the cholesterol and the red blood cells to zero by any means, but there is a drop that has been noted. So my clarifications: cholesterol cannot be made in cells without an endoplasmic reticulum, and these include the sperm. And then the Sertoli cells can actually make cholesterol, but not enough. And red blood cells, don't have ERs, and so they can't make cholesterol. And so their membrane cholesterol content is dependent on exogenous sources. They're constantly exchanging cholesterol through concentration gradients and so forth with lipoproteins and other tissues. RBCs are involved in cholesterol transport, and lowered cholesterol can result in anemia. All right, now let's look at this part of the interview where it's Dayspring again. Let's have you listen.
Cannot have atherosclerosis without a sterol or lipid being in your arterial wall. And I know that arterial wall didn't oversynthesize sterols, creating a sterol buildup. Somebody had to deliver those sterols there, and that, of course, turns out to be a lipoprotein.
All right, so he's saying that atherosclerosis, those sterols that are in the wall of the artery are the reason for atherosclerosis, and the wall itself didn't oversynthesize sterols to create a backup or a buildup. Somebody had to deliver those sterols there, and that, of course, turns out to be a lipoprotein. So this is from New England Journal of Medicine, 2003, Intraplaque Hemorrhage and Progression of Coronary Atheroma. And they say, by contributing to the deposition of free cholesterol, macrophage infiltration, and enlargement of the necrotic core, the accumulation of erythrocyte membranes, RBC membranes, within an atherosclerotic plaque may represent a potent atherogenic stimulus. This is Frontiers of Physiology 2014, red blood cell hemoglobin and heme in the progression of atherosclerosis. They talk about plaque neovascularization, where we have inappropriate angiogenesis, formation of new blood vessels. These new vessels or neovessels are leaky and prone to rupture. The extravasation of red blood cells within the plaques then could happen after this rupture, and the cholesterol content of RBC membranes contributes to lipid deposition and lipid core expansion upon intraplaque hemorrhage. This is another one, International Journal of Molecular Sciences, and red blood cells and hemoglobin in human atherosclerosis and related arterial diseases, pretty much saying the same thing about how RBCs are contributing both to inflammation and the cholesterol content in the wall. All right, so now let's go back to what he said again. I think let's just take another listen.
Atherosclerosis without a sterol or lipid being in your arterial wall. And I know that arterial wall didn't oversynthesize sterols, creating a sterol buildup. Somebody had to deliver those sterols there, and that, of course, turns out to be a lipoprotein.
All right. So again, he's saying the wall itself is not making these sterols. So this is a paper called Cholesterol Paradigm and Beyond in Atherosclerotic Cardiovascular Disease. What they note here is SREBP, remember that transcription factor, can be upregulated, turned on, right, in vascular wall subject to injury or something like stent implantation. So this transcription factor can be activated by pro-inflammatory and mitogenic factors in the vascular cells, in the walls of the blood vessel, leading to hyperactive mevalonate pathway, leading to hyperactive cholesterol synthesis, which promotes vascular cell mobilization, further pro-inflammatory and mitogenic factor release from vascular cells, and vascular inflammation. And they end by saying, targeting vascular hypercholesterolism could open a new avenue in fighting against atherosclerotic cardiovascular disease. So they're really saying that when you have injury to the vessel wall, inflammation, then you upregulate cholesterol synthesis within the wall of the blood vessel itself, which then promotes, the plaque formation and so forth. Now, we go on to another comment that he makes in part 2. Take a listen.
Jersey guy, one of my standard jokes on a lecture circuit was atherosclerosis is just the evidence of illegal dumping, where a lipoprotein, instead of bringing lipids to where we're supposed to be bringing it, was bringing sterols to the arterial wall. And it turns out in the long run, it's the number of apoB particles that primarily is what forces it into the artery wall.
All right, so I thought worth looking at here. He talks about illegal dumpings. It's almost like they're sneaking in and illegally dumping their contents in there in the vessel wall. And then this idea of these particles forcing themselves into the artery wall. I thought maybe we should spend some time looking at this and getting a little clearer as to what is causing the LDL particles to move into the wall. So this is a paper, and basically we find that 85% of arterial lipoprotein delivery to the subendothelium is estimated to occur via transcytosis. So this is a regulated process, transcytosis, whereby these lipoproteins are taken in through endocytosis, right, into the cell. And it says here lesser amounts of lipoproteins are delivered via gap junctions or other processes. So, these cells are lined up against each other, and sometimes those gap junctions, the gaps between cells, become a little loose, and maybe things can force themselves or go through those gaps. But it turns out 85% of arterial lipoprotein delivery to the subendothelium is occurring through a regulated cell process called transcytosis. Now, in addition to LDL binding, ApoB 100 contains at least 8 potential proteoglycan binding sites. The binding of LDL to proteoglycans is mediated by ionic interactions between the negatively charged sulfate and carboxyl groups of the GAGs, glycosaminoglycans, and the positively charged lysine and arginine residues in ApoB 100. I did talk about this in episode 20 of the podcast when I was talking about the glycocalyx. So here, I did hear them talk about proteoglycans inside the vessel wall, subendothelial layer of proteoglycans, and how the ApoBs get trapped there, but they never referenced at all the glycocalyx. So we have actually a layer of proteoglycans outside the wall, lining the endothelial cells. This is well known, vital, but hardly ever gets discussed because these ApoBs are attracted through ionic forces. The proteoglycans and the GAGs, the glycosaminoglycans in the glycocalyx, the heparan sulfates, and so forth, they are highly negatively charged. Okay, and it turns out there are specific residues in ApoB that are positively charged. So anytime you have the ApoBs bypassing or going through the lumen of the blood vessel, they're going to be drawn to these negative charges, right? And that's, bringing them to this glycocalyx. They're not actually ramming or forcing themselves in there. Now we get to this study here, which focuses also more on the glycocalyx. And as I said, you can go to my episode on the glycocalyx for more details, but I think it's important to emphasize what's happening here when we're talking about ApoB at the vessel wall. So as I said, the glycocalyx lines these blood vessels. It is normally quite thick and lush and acts as a kind of permeability barrier because even though there are all these negative charges in them, they're embedded well within the layer, right? And there's some attraction of the ApoBs there, but most of the negative charges are within the thick layer of the glycocalyx. However, when we degrade or damage the glycocalyx and it thins out and we expose parts of it, now all those negative charges are exposed and the ApoBs can get drawn to those charges, right? And especially oxidize apoB, because when we oxidize apoB, we change the structure again. We expose more of these positive charges on the amino acids, and it's much more positively charged than usual and gets drawn to the negative charges. We can also cause it to clump in different ways, right? So when the glycocalyx is damaged, then we lose this permeability barrier. And indeed, the apoB now gets a lot closer to those endothelial cells, which can then transcytose the LDL in. Now, here in this study, they're looking at a mouse model of atherosclerosis, and they made these mice deficient in a glycosaminoglycan called perlecan, all right? So this perlecan is not existent in these mice. And as a result, we lose that permeability barrier. And as I said, now those apoB particles can get a lot closer to the endothelial cells and get transcytosed into the cell. At the same time, because we don't have this perlecan, remember there are proteoglycans within the vessel wall itself. And normally that is what traps the apoB there because of those ionic charges. But if we have perlecan deficient mice, they don't have the glycocalyx. So, okay, we get more of the apoBs entering into the vessel wall. But at the same time, because we don't have the perlecan within the vessel wall, we don't retain the LDL there, right? So that's really what this study is talking about. And I know there are complexities here, but I feel that we should really start now to look at these nuances and not just, kind of go with, oh, it's kind of forcing itself into the wall. And if you'll note, every time you look at a diagram showing this happening, often they'll just show the endothelial cells and then maybe apoB, getting into the wall of the blood vessel, and completely missing from the discussion is the glycocalyx. And this is, really a problem here. And I think they missed an opportunity in this series to talk about the importance of the glycocalyx, especially we're going to talk about how apoB gets into the wall, right? Because we have to now pay attention to the nuances, especially if we hope to elevate the discourse here, maybe to the level of a lipid fellowship. We want to start to understand what's happening and the different factors that are contributing to the apoB getting into the vessel wall. So, I thought that I'd share that because I think it's really important. Again, details you can look up in the glycocalyx episode. Here we're talking about sphingomyelinase-induced aggregation of LDL. So sphingomyelinase is an enzyme that acts upon sphingolipids, right? Like sphingomyelin, where a lot of times in the lipid rafts. So these things connect. So this sphingomyelinase, when it occurs, it causes aggregation of LDL because it induces a massive global conformational change in apoB, exposing hydrophobic motifs that adhere to each other, cause them to clump, all right? And so now we can have aggregation of this LDL. This is about, why we have retained apolipoproteins, and it says it's been hypothesized that specific cellular and molecular programs that cause immune cells to remain in place may have evolved as a defense against tuberculosis. So I did do an episode on this, tuberculosis and atherosclerosis, episode 52. I know little people thought this was a little crazy when I did it. Why is she talking about that? There's, I think, some method to my madness, I hope. But yeah, you can go and look at episode 52 if you're interested. But basically, retained and modified apoB containing lipoproteins within the arterial wall elicit many of the same anti-migration signals as tuberculosis does. And this is another study from Nature Communications, and it looked at how the endothelial cells actually had a lot of the cholesterol crystal production that would be very toxic to the cell and promote atherogenesis. So my clarifications for this would be endothelial cells can modify cholesterol esters into toxic free cholesterol implicated in atherosclerotic cardiovascular disease. Injury to the vessel wall upregulates cholesterol synthesis inside the wall. And we call this vascular hypercholesterolism. Aside from lipoproteins, those red blood cells also contribute to plaque cholesterol. LDL is mostly transcytosed through the endothelial cell. It's not forced in. And apoB has positive charges in certain amino acid residues, which are attracted to negatively charged GAGs in the glycocalyx. Again, you can look that up on episode 20. All right. This is the part I wanted to get into a little bit. And this is the part where I think they kind of missed out talking about, because they talked a lot about exchanging cholesterol and, cholesterol being transferred to different parts of the body and so forth. But they never really looked at the different pools of cholesterol in the body. And I think this is very important when we're thinking about cholesterol, right? Because we actually have 3 distinct pools here. I did talk about this on episode 46, but let's just do a quick summary here. We have the accessible pool of cholesterol. This is in equilibrium with the endoplasmic reticulum. So this is under control, right? Homeostatic control with SREBP2. This is very important because this is the cholesterol we're talking a lot about when we're talking about, cholesterol being transferred and, taken up by cells and so forth. We're talking about this accessible pool here. Now, we also have a sphingomyelin associated pool. And this is generally not accessible. You can't use this, all right, because it's associated with the sphingomyelin, particularly in the lipid rafts. We need those lipid rafts for those receptors, right? However, if you treat the cell with sphingomyelinase, right? And there are certain pathogens, microorganisms, immune cells that can produce sphingomyelinase. Then you basically disrupt the rafts, the lipid rafts, right? And the cholesterol that used to be in the raft, now that can go into the accessible pool. So that's really important. And I thought I'd add this from Cardiovascular Research 2009. Sphingomyelinase activation occurs in different cardiovascular system cell types, cardiomyocytes, endothelial, vascular smooth muscle cells, mediating cell proliferation, cell death, and contraction of cardiac and vascular myocytes. So we have the sphingomyelinase from microorganisms, immune cells, but also different cardiovascular type cells. And when this is activated, we're actually going to increase the accessible pool of cholesterol here. So inflammation, for example, can, in some sense, upregulate or increase the accessible pool of cholesterol. And then we have the essential pool, and that you can't access. It's very hard to get any access to the essential pool, because if you were to touch that, then essentially the cell would die, right? So that's necessary for cell survival. So I think it's really important to think about the different pools, because whenever they talk about cholesterol and cholesterol being transferred, you have to think about, okay, there are different pools, and mostly we're talking about this, the accessible pool, and in some circumstances, we'll be talking about the sphingomyelin associated pool. All right, so remember that homeostatic control of cholesterol is regulated by ER levels of cholesterol. Those RBCs don't have ER, so they don't make cholesterol, and they have no feedback for homeostatic control of cholesterol content. And then I threw this in, RBCs interact with macrophages. Very interesting, another rabbit hole probably to go down, but actually worthwhile. Maybe I'll do an episode at some point, but not now. Okay, so moving along. Okay, we have this. Let's take a listen.
They shrink, but there's one protein they never lose, and it's the one that has the most massive molecular weight, apolipoprotein B. So that's why they are never going to be as dense as an HDL particle, because an HDL doesn't have this monstrosity high molecular weight apoB on it. It's got other things, far less lipids. But to some, the LDLs, IDLs, VLDs are always going to be way more buoyant because they do have a little bit of an anchor on them, creating to their density is that apoB.
All right. So here I think he's just getting a little fuzzy here, right? And I thought it'd be important to clarify. No, he clearly understands this, and I think just didn't come out quite the way he wanted. So he's saying that ApoB has a massive molecular weight, but he's also saying they're never going to be as dense as an HDL because an HDL doesn't have this monstrosity high molecular weight apoB. So, and again, I'm sure he understands this. I think it just came out wrong. So let's just look at this very quickly. My clarifications here: apoB 100, glycoprotein 4,500 plus amino acids, 550 kilodaltons, huge, right? He called it a monstrosity, and that's true. However, the lipoprotein density is actually based on the ratio of proteins to lipids. Okay, so LDL has a lot more lipid components, whereas HDL has far more protein components, right? Over 200 or more proteins, right? And so because it has way more proteins than its lipid components, the HDL density is higher. The LDL does have this big molecular weight apoprotein on it, but it has a lot of lipids as well. So it is more buoyant, right? And that's, I'm sure what he was trying to say just got maybe a little bit, you know, fuzzy. All right. So the next part, also just a clarification.
The apoprotein is the thing that kind of gives it its signature. So, for example, the chylomicron has a B48, the IDL, VLDL, and LDL have a B100, etc. That's just called the apoprotein. It's once the apoprotein, and I assume it's covalently bound to the lipoprotein, that becomes the apolipoprotein. And we abbreviate that apo, fill in the blank.
Yeah. So if I took a VLDL particle, and later on I'll tell you, boy, on a VLDL, you're going to find ApoC1, ApoC2, ApoC3, ApoA5, including apoB, but it's going to lose everything but apoB as it's transferred. It'll lose most of the other ones because they're transferable. They can jump on different lipoprotein if they so.
Okay, so this is very important. Many of these, not the apoB is always going to be bound to its, lipoproteins, but these other apoproteins are transferable. And here, Peter Attia was just musing. He says, "Oh, I assume they're covalently bound." But there are a number of things here that, kind of caught my attention. And what we have to remember, if we go back to first principles, I think that's always important, right? First principles thinking. Covalent bonds have shared electrons between atoms. So this makes them very stable. And in fact, they're one of the strongest bonds. And to break those bonds would take a lot of energy. I know I'm always talking about energy, right? I'm interested in metabolism. So anyway, but in protein folding and lipid structures, the hydrophobic bonds predominate, which is great because these hydrophobic bonds would then allow those apoproteins to be transferable. Remember, it's very important that they can be transferred. If we had covalent bonding, it would be a huge amount of energy every time you needed to break a bond to transfer an apoprotein, right? Just think about this. It's like a lot of work. Maybe it's because I'm lazy. I'm always thinking about, is that going to be a lot of work, right? But if we go back to first principles, it's highly unlikely that we're going to have covalent bonding there. Most likely some hydrogen bonds, hydrophobic bonds, yeah. And that would help with the transfer of apoproteins. Okay. Next part. Here we go.
True, although I've heard it speculated on, but truthfully, I've never seen the data with my own eyes. Do statins have selectivity for the liver?
Sure.
So that would be another unintended benefit, right?
Okay, this one I have to say did take me by surprise. So Attia asks, do statins have selectivity for the liver? And Dayspring says, sure, and he's quite confident there. So, as I said, I'm very much interested in immunology, immunometabolism. So I'm always looking at these studies where, they use statins on immune cells because, if we modify these different metabolic pathways, then we can see how cell function changes in immune cells. So I would read tons of papers where they would use statins all the time on immune cells. So here's one from immunology where they look at immune modulatory effects of statins. And here's another one, immunomodulatory effects of statins on macrophages, my favorite cell. But, again, statins are able to have effects on different types of blood cells. Statins also can impact head and neck cancer cells, right? And here's one from Journal of Endocrinology Investigation, 2007, role of cholesterol biosynthetic pathway in osteoblastic differentiation in bone. So they say, by using statins, many studies have been performed in order to shed light on the role of cholesterol on different cell types and among these on bone cells. So they're quite aware too that we often see lots of studies of statins on bone cells. And do you remember in the earlier part, Dayspring talked about the nose cell, and both of them would go on and on. I found this was repeated several times. Sorry, I had another coughing spurt, but let's get back to this. They would go on about the nose cell and how it could make its own cholesterol. And they kept coming back to this nose cell. Let's take a listen.
So if I'm a nose cell, I don't need some lipoprotein to come and deliver cholesterol to my cell because I need cholesterol in my nasal cell membranes. That cell will make cholesterol.
And then
my nose cell that I talked about before doesn't need HDLs or anybody else to deliver cholesterol to it. No other cell does, except those steroidogenic tissues.
In other words, to be really clear and specific, you're sloughing off endothelial cells in your nose every day. Well, you have to replace them. The lion's share of the cholesterol requirement is to make a cell membrane. It's just, it has the machinery. It has the machinery within the nucleus to produce that, just as it's producing other structural proteins.
Right. So, and this is what people just translate low cholesterol plasma measurements to think you're screwing up cells throughout the body, and you're not.
Okay. So I thought it might be fun here just to find, some nose cells and see what the effects of statins would be on those nose cells. So I kind of looked around and I found this article on cholesterol biosynthesis modulates differentiation in murine cranial neural crest cells. So the neural crest cells actually make your nose. And this is looking at BAMS, which is a syndrome consisting of arrhythmia, which means absent nose, eye defects, and hypogonadism. And this is caused by a gene mutation. And so what they did was they used fatostatin. Okay, this is not a statin, it's an SREBP inhibitor, but it does lower your cholesterol levels. And they also use fluvastatin, that's a regular statin, okay? So here with fluvastatin, we observed a diminished ability of cranial neural crest cells to differentiate into chondrocytes, right? Your nose is mostly cartilage, so the chondrocytes actually become the cartilage. And so what we find here is that when we give statins, well, we're not able to form a nose because probably you just aren't able to make the nose, yeah? So I thought that was a fun example because they talked so much about no cells. And basically, again, we see here that no, the statins are not liver selective at all. And I think they know it because later, Dayspring says, at least it's been theorized. And Attia says, in an ideal world, you wouldn't want to inhibit cholesterol synthesis in a single tissue outside the liver. Amen. In an ideal world, right? But, that would be a fantasy right now. So my clarifications for this, statins have effects on a wide range of tissues in the body. Their effects are not liver selective. Okay, let's move on to the next part.
Sure. So certain cells can certainly transform cholesterol into reproductive hormones or adrenocortical hormones. Certain cells, hepatocytes, can transform cholesterol into a bile acid. I don't think there's any other cell that can change cholesterol into anything else. So when people talk about cholesterol metabolism, there is no cholesterol metabolism. It can be converted into something in specific tissues, but it can be excreted. That's it. There's no.
All right. So what I want to say here is that when I listened to the interview, again, the scope was limited to functions of cholesterol with respect to cell membranes, organelle membranes, and steroids, end products of cholesterol metabolism, right? So the steroid hormones like the sex hormones, glucocorticoids, and so forth. They really didn't talk at all about a very, very important distinct function of cholesterol, which is immune regulation. Completely miss, right? But it changes everything. And I think it's highly important that, they consider this part, because if you're just looking at structure of cell membranes and steroids, then you're missing a much bigger picture. So here is something that I discussed on episodes 46 and 50. And we're looking at immune function of cholesterol. Here I focus on the innate cells, macrophages. Yes, I love the macrophages, but we do also have this impacting adaptive cells. But just for now, let's look at this. Macrophages rapidly upregulate cholesterol synthesis when activated. And it turns out interferon signaling generate interferon responses that downregulate cholesterol biosynthesis and increase cholesterol storage in the form of cholesterol esters. Macrophages shift their cholesterol metabolism in a context-specific manner to facilitate specific effector functions and ensure the generation of particular forms of inflammation. Interferons versus interleukin-1 beta, for example. So what we're seeing here is that by shifting their cholesterol metabolism, we are generating different cytokine signaling, right, to bring on specific forms of inflammation. It's very important in the immune function of cholesterol. The other thing that I think is missing in their consideration is the role of metabolites in biological functions, right? So again, here I show you the pathways for cholesterol synthesis, and they focused on the endpoints, the steroid hormones, the bile acids. They didn't talk about oxysterols. I do have an episode on that. You can look that up. And then I think it was just an oversight. They forgot about vitamin D. I'm sure they're well aware. You all know it's derived from the synthetic route to cholesterol synthesis, dependent on the last enzyme in the Candet-Russell pathway. Okay, but they're focused on these endpoints. What they're actually not looking at are the metabolites, right? So protein prenylation, geranyl pyrophosphate, and farnesyl pyrophosphate, they are products of the cholesterol pathway, HMG-CoA reductase pathway. This means that statins, which inhibit HMG-CoA reductase, inhibit the production of both cholesterol and these isoprenoids, right? These are called isoprenoids. So what's so important about these isoprenoids? Well, this is from a paper from 2007, and it says, post-translational prenylation of proteins with isoprenoid lipids is one of the most widespread and well-recognized post-translational modification of proteins in eukaryotic cells. So in this study from ACS Chemical Biology, in normal healthy cells, the function of the RAS superfamily of GTPases in diverse cellular processes such as growth, cell movement, protein trafficking, critically depends on their presence in the correct cellular membrane. And here we have a diagram from that study, and it's called Protein Prenylation, Enzymes, Therapeutics, and Biotechnology Applications, right, from 2015. And they basically tell you how we sort proteins in the cell membrane. When we attach these isoprenoids, the farnesyl and the geranyl isoprenoids, to the protein, it helps their localization to specific parts of the cell membrane, right? And this also will help define polarity in the cell membrane. So this is highly, highly important for functioning, for signaling. So when people talk about cholesterol metabolism, there is no cholesterol metabolism. It can be converted into something in specific tissues. And by this, they're talking specifically about the steroid hormones mostly, right? And it can be excreted, and that's it. So it's completely missed out also the metabolites. Now, here's a reason, concrete reason, as to why this is important. Let's take a look at this. A fundamental role of pancreatic beta cells to maintain proper blood glucose level is controlled by the RAS superfamily of small GTPases that undergo post-translational modifications, including prenylation. This covalent attachment with either a farnesyl or a geranyl group controls their localization, activity, and protein-protein interactions. Most small GTPases involved in insulin trafficking and secretion are required to be prenylated to function for their biological role and interaction with their respective effectors. So again, you'll see that these GTPases, they're not going to work and, then help with insulin trafficking and secretion if they are not prenylated. So again, people talk about studies where, there seems to be some correlation between use of statins and diabetes. Oh, that's no big deal. That's probably not important. Yes, it is. No, it isn't. I don't, I really focus on mechanism. For me, I like to know what might be going on. Again, I'm not saying this is the reason there might be an increased incidence of diabetes with statin use, but it could be one mechanistic pathway for that to happen, right? If we're not prenylating these GTPases correctly, then we might actually be interrupting insulin trafficking and secretion. Oh, and here, another study, but this one's talking about mTOR, right? Rep-G proteins and the activation of mTOR. I actually talk about this in episode 21. I do talk about mTOR and cholesterol and how that's related. That was a whole episode on mTOR, so if you want to take a listen, go ahead. But remember the small GTPases that are important in mTOR regulation and activation, right? And if they're not prenylated properly and they don't work, then your mTOR is going to work either. So again, might this be related mechanistically to statins' effects on muscle? That's something to consider. I'm always much more interested when there's a mechanism that's proposed. All right, my clarifications here then. Besides cholesterol, the mevalonate pathway is important for the synthesis of steroid hormones, oxysterols, isoprenoids. The metabolites of the pathway regulate cell function and metabolism in fundamental ways. Halting the mevalonate pathway not only means decreasing the end products of the pathway, it also decreases the metabolites of the pathway, and decreased metabolites of the mevalonate pathway impact cell regulation, proliferation and growth, signaling, metabolism, immune function, beta cell function, muscle function, probably. Right? So those are things that I think we need to start looking at bigger scope, not just one part, right? Okay, let's go to this.
This is the metabolic response to sepsis, infection, trauma, you name it. Enormous drop in HDL cholesterol. And I think we could look at that today and say it's very likely that what we were seeing was in that period of profound physiologic stress, the body is greatly ramping up its hormone production with corticoids and others. And that would be one of the situations where cells were actually, HDL was now delivering cholesterol to the adrenal glands in a period of, because that's about the most physiologically stressful thing that an organism can respond to. Again, I don't know if that's been documented, but it seems to me pretty logical that that would be at least the most plausible explanation for why HDL could plummet in patients who are going through that degree of stress.
Okay, that's true. Very good point. But again, you see they focus on the steroid hormones, right? The endpoint of the cholesterol synthesis, and we're not looking at other functions. And I just wanted to point out that HDL is very important for clearing bacterial toxins, supporting corticosteroid release, which is what he mentioned, decreasing platelet aggregation, inhibiting endothelial cell apoptosis, reducing the monocyte inflammatory response, and inhibiting expression of endothelial cell adhesion molecules. So, I did talk, actually, I did have a episode on cholesterol. I forgot to put it here, so you can go look for it. But this is a very famous study. I think everybody's seen it by now, right? It was very exciting when it came out. And it looked at the role of HDL in immune defense. And what we have here is LPS produced by bacteria, which, if it gets to the liver, can damage the liver. There's a lot of inflammation going on, and we get fibrosis of the liver. But we have HDL to the rescue. So we have intestinally produced small HDL, which can then bind to the LPS. And as a result, it protects the liver from inflammation and fibrosis, right? Again, very exciting and well-known study by now, but looking at the immune function of HDL. So my clarification simply here, HDL is in the process of being redefined. It's likely better defined by its proteome. They talked a lot about its lipidome, but I think it's going to be more important to look at the proteome. And I've been looking closely at the HDL Proteome Watch database. HDL is a platform that aggregates various proteins to impact biological functions. And it is involved in immune modulation, antioxidant activity, hemostasis, cell binding, and so forth. All right. And then this was just a simple question that Peter Attia asked. And it's basically, has anyone ever looked at RBC cholesterol concentration or even size in FH patients? Because a hypothesis would be, especially FH patients who have FH as a result of LDL receptor deficiencies of some sort, you'd think there'd be more free diffusion of cholesterol from their LDL into their RBCs. And just very quickly, here's a study looking at RBC shape and size and how they're modified in FH. But this brought up, just other thoughts in my mind of how, again, the cholesterol content in the RBC is going to impact their function. So this study here looks at cholesterol deficiency and how it causes impaired osmotic stability of cultured red blood cells, right? So if you have too little cholesterol, then it's going to impact the stability of that cell. Here's another one, looking at red blood cell membrane cholesterol as a key regulator of sickle cell disease microvascular complications. And very quickly, sickle cell anemia, we find we have actually low plasma cholesterol, low cholesterol, and all the lipoproteins. But there's increase in cholesterol content on the RBC membrane. And then there's concurrent low levels of LCAT, so it doesn't get transferred to HDL. And that HDL, again, modulates cholesterol and phospholipid ratio for oxygen transport. So very interesting, but here, main thing to note is that there is increased cholesterol content on the RBC membrane, which makes the membrane, what? By now you should know, stiffer, right? More cholesterol, stiffer. So what happens is that, these cells, they are going to have more cholesterol and become stiffer. Now, red blood cells need to be deformable because they need to be able to squeeze into tiny capillaries and little blood vessels. So it's very important to have the ability to deform, right? Be pliant. If you have more cholesterol on the RBC membranes, they're going to be stiffer and less deformable. And this might be related to the sickling effect when we have microvascular complications in sickle cell anemia. So very important there. Okay, quickly again, moving on to this next point.
They're fundamentally concentrating protein as they get. I mean, because when you go from chylomicron, even though they're not the same lineage, so I want to be very careful. You'll explain this in detail. You do not go from a chylomicron to a VLDL to an IDL to an LDL to an HDL. There are three separate lineages I just described. But
chylomicrons, which intestinally produce, VLDLs, hepatic produce, and
is the thing that kind of gives it its signature. So, for example, the chylomicron has a B48, the IDL, VLDL, and LDL have a B100, etc.
And virtually in a fasting state, all of the triglycerides are not in an HDL, they're not in an LDL. We're not measuring chylomicrons because they're in a VLDL.
Okay, and by that he means apoB 100, right? Here they're talking about different lineages of those lipoproteins. And they make a distinction between intestinally produced, which hold the apoprotein B48, and liver produced, which hold B100. And they're saying that it's only the chylomicrons that have the B48. As you see here, the IDL, VLDL, and LDL have a B100. And he says in a fasting state, all triglycerides are in VLDL and therefore actually having the B100. And he also later, this Dayspring, he talks about chylomicron half-life is minutes and the VLDL half-life is a couple of hours. Only a few particles are persisting beyond that average half-life or so. So again, they're very distinct here about the different lineages of the lipoproteins. And I thought we should look at this from the Journal of Internal Medicine. And it says apolipoprotein B48 metabolism in chylomicrons and very low density lipoproteins. So what we see here, the intestine secretes apoB48 containing particles, not only as chylomicrons, but also directly into the VLDL1 and VLDL2 density ranges, both in the basal and during dietary lipid absorption. Okay, and whilst chylomicrons in the circulation were mostly cleared within a 12 to 14 hour time frame, the same is not true of intestinally derived lipoproteins in the VLDL density range. So basically, they found that across the day, the apoB48 particles from both basal secretion and postprandial production accounted for about 23 to 30% of the total number of VLDL1 and VLDL2 particles in the circulation. It's about a quarter to a third of the VLDLs. This is the reference. My clarifications here: intestinal lipoproteins have apoB48 as the associated apoprotein. True. These include chylomicrons and up to 30% of the VLDL1 and VLDL2 particles in circulation. Chylomicrons are mostly cleared within 12 to 14 hours of fasting, not the intestinal B48 containing VLDLs. All right, now moving along very quickly. Let's see, we get to this.
Around forever until the LDL receptor clears an LDL by binding to apoB. The reason chylos, VLDLs, and IDLs get cleared so much more quickly than LDLs is the ApoE content, which is a megaligand for the LDL receptor. The LDL receptor is really an apoE receptor, and there are other ApoE receptors too. So that's why those particles don't last.
And just to interrupt you for a sec, ApoE greatly amplifies the efficacy of that ligand, the apoB ligand.
It just is it's a preferred ligand for either an LDL receptor or other. They're called LDL receptor related receptors.
So what percent? I'm sorry, I want to come right back to what you're saying, but just because I know I'll forget to ask, what percentage of LDL particles also co-express ApoE?
Yeah, so if you were lucky enough to have that genetic gift, and your LDL haplocyclated, its half-life is pretty much the same as an IDL. They're gone. So if they're gone, guess where they can't wind up? Yeah, you have enhanced clearance. Your apoB, your LDL particle level will be much lower. You don't get heart disease. In an average population, it's about 3 to 4%. But I guarantee you there are, depending on genes you inherit, some people have probably had a lot of ApoE on their LDLs. And of course, I would bet if they were studied genetically, they don't get heart disease, because it's being cleared, all those particles.
All right, so this part is a bit more complex, but I thought worth commenting on. So ApoE, this is a paper from 2016, ApoE from cardiovascular disease to neurodegenerative disorder. I think most people know that there are 3 isoforms, ApoE2, ApoE3, and ApoE4, that differ only by a single amino acid between them, and they have different functions. So it says here, ApoE2 and ApoE4 increase the risk for heart disease. E2 increases atherogenic lipoprotein levels, binds poorly to LDL receptors, and ApoE4 increases LDL levels, binds preferentially to triglyceride-rich, very low-density lipoproteins, leading to downregulation of LDL receptors. And I think everyone knows that ApoE4 also seems to increase the risk for neurodegenerative diseases. All right. So when we talk about ApoE and we're looking at risk, I think it's important to also consider the isoforms here, right? And how they can vary in different forms of dyslipidemia. Now, as he was saying, most people think that there is really no ApoE on LDL. Well, this paper says, well, classical knowledge is that LDL does not have ApoE. Nevertheless, since ApoE binds to lipids through its C-terminal domain, it seems difficult that it binds to HDL, VLDL, IDL, Lp(a), but not LDL at all. Indeed, lipoproteins isolated by flotation sequential ultracentrifugation showed that ApoE represents 0.4, 0.1, and 0.38% of the total mass of VLDL, HDL, LDL. Lipoproteins isolated by anti-ApoE immunoaffinity chromatography showed the presence of 21, 19, and 5 molecules of ApoE in a portion of VLDL, HDL, and LDL, respectively. So we do see binding of ApoE to LDLs, not as much as the other lipoproteins, but it does occur. And okay, This is a lot of text that I put on here, but this is basically just to show that, again, there are all these differences between the different isoforms. So, I think when we talk about ApoE, we have to understand that the different isoforms will confer different structural and charge affinities, right, in the lipoproteins. So, for example, ApoE is associated with higher apoB, total LDL and remnant cholesterol levels due to its preference for VLDL and its higher production rate and higher VLDL lipolysis activity. And then we also see there's increased level of LDL in ApoE4 carriers due to downregulation of the LDL receptor expression. And then we also see with ApoE2, because of its structure, there's a disruption of a salt bridge that lowers the positive potential and alters the receptor binding domain, which affects drastically ApoE2 affinity for its receptors, less than 2%, but not its affinity for heparan sulfate proteoglycans, right? The GAGs, right? So the GAGs to the rescue here, but otherwise, it has less affinity for its receptors. ApoE2 also inhibits the VLDL lipolysis significantly more than ApoE3, E4, and so forth. So again, just to show you that the different isoforms are going to have different, structural consequences and also charge interactions with the receptors and so forth. This paper from 2013 looks at plasma ApoE, and they note that there is measurable concentration of ApoE in LDL that is distributed throughout its conventional density range that includes the intermediate density lipoproteins and the light and dense LDL. So actually 10 to 25% with IDL and LDL. And then they go ahead, give this nice graphic here, looking at the percent of plasma LDL. Turns out about 82 to 97% of LDLs don't have ApoE or ApoC3. Now, ApoC3 actually is associated with higher cardiovascular risk, higher heart disease, right? So it's not a good thing to have. So 82 to 97% of your LDLs don't have ApoE or ApoC3. 0.4%, up to 0.4% of LDLs have ApoE alone, no C3. Then you have 1 to 12% with ApoC3, no ApoE. And 0.5 to 4% of LDLs have both the C3 and ApoE. And what we note here, importantly, is that when you have LDLs with the ApoC3, I told you that will give you a higher risk for heart disease, coronary heart disease, right? Higher than just LDL alone. However, if you have LDL with ApoC3 and you have ApoE, then you have a markedly lower risk for heart disease as compared to LDL with just ApoC3 alone. Okay, so the interactions between the different apoproteins is also important. And they note ApoE isoforms have structural differences that may modulate their function in LDL. Also, triglyceride-rich lipoproteins are cleared via ApoE through heparan sulfate receptors, synakin 1. That's in the glycocalyx episode. And then I just wanted to point out there are other ApoE receptors, the VLDL receptor and ApoE receptor 2, part of the renin pathway, which is another rabbit hole to go down someday. So my clarifications here, the different isoforms of ApoE confer different risk profiles to atherosclerosis and heart disease and neurodegenerative diseases. In addition to LDL receptor and LRP, we have VLDL receptor and ApoE receptor 2, but ApoE also binds the synakin 1, a GAG, for clearing of triglyceride-rich lipoproteins. ApoE receptor binding is subject to its structure and electric charge. ApoE impacts lipolysis of triglyceride-rich lipoproteins and downstream subclasses of lipoproteins and their functions, right? So you don't look at it in isolation because, we want to see downstream how it would affect those lipoproteins, right? So not to consider it just in isolation. And also, apoprotein associations may impact their function, and their effects must be considered in this light, right? Versus only in isolation. Again, if it's associated with certain other apoproteins, the risk for heart disease, for example, may change. Right? So those are some things just to note with regards to ApoE. Now let's move on to the next part.
So I explicitly went over that the functional purpose of chylomicrons and VLDLs is to deliver energy in the form of triglycerides, the adipocytes and myocytes, and phospholipids, not to deliver cholesterol to any darn cell in your body. So spend your time reading on it. That's what they do. You could even make the case that if they're not delivering cholesterol, why is cholesterol even in their particles? And it goes back to something what Peter said. These particles have to be spherical. So when a VLDL or an enterocyte is starting to lipidate apoB 48, or especially the liver, apoB 100, if you put cholesterol in that, and we have proteins that do that, microsomal triglyceride transfer and other cellular lipid transport proteins, by putting cholesterol on the apoB, it becomes a spherical particle. So all primordial VLDLs and chylomicrons are first just very cholesterol-rich spherical particles. They don't have the triglycerides yet. Then when they're spherical particle, they can really fill up with their triglycerides. So the cholesterol is in there for a structural property to make them spherical particles so that they can carry more triglycerides. And that's why when they go out, they become smaller spherical particles that are triglyceride depleted, and they just bring their cholesterol back to the liver or the intestine, and they do whatever they do with it. So that's why cholesterol's in there. They're not bringing cholesterol to my nose or your kidney or any place else because those cells need cholesterol. Those cells will make it, or they'll get it.
Okay, so let's just make sure we understood what he said. So he's saying that those lipoproteins aren't really there to deliver cholesterols. Well, if that's the case, he asks, why is cholesterol even in their particles? And it goes back to what Peter said. They have to be spherical. So by putting cholesterol on the apoB, it becomes a spherical particle. So all primordial VLDLs and chylomicrons are first just very cholesterol-rich spherical particles. They're mostly cholesterol to make them spherical. That's what I'm understanding here. The cholesterol is there for a structural property to make them spherical particles, right? So I think I got what he tried to say there. And, when I heard that part, I stopped a little bit and I thought, well, I'm not a lipid specialist and I don't have any research background. I'm not a structural biologist by any means. Um, I don't know. Wow, really. And sometimes I read papers or I come across something and I get really intimidated because it's not my field and it seems very complex. So here we're talking about structure of a new lipoprotein and how it forms, and that seems very involved. So I get a little bit intimidated when I read such complicated things or hear such complicated things. But some of you know I have a classics background, and so I remember Aristotle and his idea of going back to first principles, right, from the Greek word arche, to go back to the beginning. So in the science of nature as elsewhere, we should try first to determine questions about the first principles. And so whenever I get intimidated or I don't understand something, it helps for me to just think through my first principles. And in this case, I found it really helpful because I suddenly remembered my cells. And my cells are these spherical structures formed entirely through physical processes such as intermolecular forces and thermodynamics, right? These amphipathic compounds disperse in aqueous solution to form these globular, these spherical structures that we call micelles, as you can see here. And you'll note there's no cholesterol there. There's no cholesterol needed there. So I think that this might actually hold a clue for all of us. And I think that here is where, first principles might triumph a little bit. So, I think we can hear the same celebration of first principles with Dayspring.
Rutgers. Such medical school was inconsequential. I learned everything in Rutgers pre-med, at least the biochemistry and the physiology anyway.
So there you go. I mean, I think it's really important sometimes not to get too caught up in maybe the complexity of things, and we can go back to the basics, especially if you have a strong basic background. This can be very helpful to, thinking through some of these more complex problems. So looking at apoB lipidation, we see here in this paper that the addition of phospholipids to this site may be important and sufficient for the assembly of secretion-competent B lipoproteins, phospholipids, right? Not cholesterol. Again, these proposed micellar structures, yay, first principles, would have an external surface of relatively randomly oriented hydrocarbon chains with certain regions stabilized by the head groups of phospholipids again, all right? And here, Journal of Biological Chemistry 2015, we demonstrated that the first 1,000 amino acid residues of human apoB 100 are required for the initiation of apoB containing lipoprotein assembly, and that this primordial apoB particle is phospholipid rich, okay? So yeah, it turns out that it's not cholesterol rich, and it's not cholesterol rich because we don't really need cholesterol to form spherical structures, that micelles are really naturally how these amphipathic and lipid products kind of aggregate in solution. And then I decided to investigate, curvature of membranes, because even though we know that micelles will make them spherical, I just wanted to, look at curvature of membranes. And I thought Dr. Attia would be interested in this because he has a background in mechanical engineering, and my brother studied mechanical engineering when he was in college, and he's interested in these things. So maybe I'm projecting here, but I think he would be interested in looking at curvature of membranes. So I threw this in, and it says for cellular membranes, positive or negative curvature is determined by curve directionality toward or away relative to the compartment of volume contained by the membrane. So positive curvature builds a sphere, so it's kind of round like this, while negative curvature is in the opposite direction, like at the neck of a vesicle budding. That's interesting. It turns out that cholesterol has intrinsic negative curvature. So it's actually kind of anti-spherical. So my clarifications here, primordial apoB is not actually cholesterol rich. It appears to be phospholipid rich. The lipids aggregate in spherical structures through physical processes, so those micelles. Cholesterol does add rigidity to membranes, and cholesterol causes negative curvature to membranes. So actually it's anti-spherical and is involved in the formation of budding structures, okay? So I think important to remember that. All right, let's listen to the next part.
Vast majority of your apoB gets catabolized because it's unused. So people always, oh, what produces increased apoB? Nothing. Your liver makes way more apoB than any human can ever use.
Why do we think that is?
I don't know. People just assume, hey, if you're making too much of something, you got to be increasing the components. Except one component we make too much of and never use is apoB.
Yeah,
Yeah, okay. So I think Dr. Attia was a little puzzled here too. Let's take a look. This is from Trends in Endocrinology Metabolism 2013, the regulation of apoB metabolism by insulin. And we see here is a diagram from that paper, how insulin downstream of its different pathways affected will impact apoB translation, lipidation, and apoB secretion. Here is one from Reproductive Biology and Endocrinology, 2016. Apolipoprotein B is regulated by gonadotropins and constitutes a predictive biomarker of IVF outcomes. And we find that apoB synthesis and secretion are regulated by several hormonal factors in hepatocytes, such as growth hormone, insulin, adrenocorticotropic hormone, and thyroid hormones. The role of LDL receptor in apolipoprotein secretion, as I said, Journal of Clinical Investigation 2000, the LDL receptor mediates degradation of apoB. And my clarifications would be apoB synthesis is regulated by a variety of factors, most famously insulin. Other regulators of apoB synthesis include gonadotropins, thyroid hormones, growth hormone, ACTH. ApoB synthesis also depends on exchangeable apoproteins, and there's the reference there. Lipid stores in cytosol or intracellular triglycerides, and there's the reference. And the LDL receptor facilitates degradation of nascent apoB. So let me stop sharing because that was just my little signal to myself to stop there, because I had like, I don't know, 200 plus slides and I got through maybe 150 something there. And you can see why it was taking me such a long time to come out with this episode. I didn't have time to go into the last two episodes much. So in any case, I think this is enough to give you a sense of the series. What I want to say is that I do applaud Doctors Dayspring and Attia for their stated goal of educating the masses and bringing the forefront of lipid science to the public. Their intention and efforts are admirable. However, as the commentators, Check 2 noted, and this was the person, if you remember, who made comments on their cholesterol chemistry, that videos like this one above are so important and can even save people's lives. Amen to that. I certainly agree. I am very worried, however, that if I can find so many mistakes on things I have a good knowledge of, how can I trust the parts I am less familiar with? And I can certainly take his point, right? Because it does open you up to doubt. When I started this podcast, people were surprised, I think, at the approach that I took. Why was I spending so much time on what seemed like basic knowledge, basic stuff? Why wasn't I talking about the big, important topics, interviewing popular guests on the podcast? I've said many times that what concerns me is the fuzziness around many discussions that I hear on science. We're apt to throw out vague, all-encompassing blanket terms like inflammation and insulin resistance without dialing down to what they really mean and imply. Before we get to the big topics, I thought I'd just go through the basics so we're all on the same page and talking about the same thing in order to prevent futile and unproductive conversations. Now, those of you who have been faithfully listening in on every episode, I really want to thank you. It's not easy to go back to the basics while eschewing the glamour and novelty of grander topics, but it helps us build a community that truly cares and defends science over populism and a culture of showmanship over substance. Like Doctors Attia and Dayspring and many others, my goal is to change the medical field through education. I love teaching. I love interacting with other curious minds. And that's why I'm always happy to meet all of you listeners at my live stream events. I really enjoy your questions. And my approach is to create a space for genuine inquiry and discovery. I always say there are no stupid questions. There are a lot of strong opinions out there, but I've never found that disparaging others or insulting them a useful way to educate them. On the contrary, it actually turns people away and closes their minds, I think. So I try to hold a space for different perspectives because it helps me see where we deviate into fuzzy thinking and also brings up new ideas and questions that I myself may not have considered before. It's not easy, so I appreciate how Doctors Attia and Dayspring are involved in educating the public and other medical professionals. There's such a need for this. I mean, you can hear how frustrated they were when they talked about how they had to fight cardiologists and other colleagues who had a fraction of their expertise, how they were seen as the crazy ones because of their non-orthodox approach to the lipid panel. So they know what it feels like to be marginalized in that sense. And I'm sure that's why they strive so hard to change those dynamics. Science is, I love science, but science is truly beyond me. There's actually very little real science in medicine. Medicine today is mostly about algorithms, guidelines, which are determined by observations, correlations, selected studies, right? So, for example, we observed when we gave this drug, say a statin, these things happened. It was correlated to these outcomes. Let's say increased incidence of diabetes. Mechanism? Oh, we don't know. It's not important. Don't worry about it. And that's really frustrating for me. There's so much I don't understand and need to learn. And I am grateful to and in awe of the dedicated scientists who forge paths ahead for all of us. And those are my real heroes because they know the importance of detail and rigor. And while the entire world seems focused on being right and showing how they are more right than everyone else, these scientists wake up every day and go to work to prove themselves wrong. They abide by scientific principles grounded in proving their own assumptions and hypotheses wrong. Pretty badass, right? I mean, being wrong is not seen as a weakness, but a contribution to science and an essential building block to our understanding of the world. There is no shame in being wrong. And my big worry is that I should get to a stage where I would be so consumed by self-importance that I should forget our human propensity to make mistakes. And I made many, 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 many mistakes. I've stayed up many, many nights worried about fact checking myself over and over every time I put out an episode. I have no team, no research department, no one to make killer show notes, and I've sweated over fact checking myself every episode, which I used to put out every week in the past while working a full-time job. In fact, I got to get going soon. So I'm sure despite that, there are probably many, many, many mistakes that I have made. But I hope that the standards that real scientists have are those that we'll all try to hold ourselves to. So I'm grateful. I'm grateful to Doctors Attia and Dayspring for their willingness to share their knowledge and expertise. Their reputations precede every talk or presentation they give and make so many people assign more weight to their content. So it's heartwarming to know that they too have high standards and fact check everyone who goes on their show or on their journal. And I hope they continue to uphold those admirable standards. My own contribution here today was to merely clarify some points and maybe to open up a bigger discussion on the disparity between principles in science and medicine today. I hope you found this episode helpful. Signing out now from VLMD Rounds, I'm Dr. Vivian Lowe, and I sing the body electric. Goodbye.